بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 7.4. We continue in techniques of integration, and this time we talk about integration of rational functions by partial fractions. So here we deal with rational functions. What is a rational function? It is a polynomial over polynomial. So for example, this is a rational function, polynomial of degree 1 over polynomial of degree 2. If we add these two rational functions using the formula a over b minus c over d equals bd, and here ad minus bc, and we expand to x plus 4 minus x plus 1, we get x plus 5 here. So now, if we have the integral, if we want to find the integral of x plus 5 over x squared plus x minus 2, we can write this rational function as partial fractions, as sum of two fractions. We call them partial fractions like this. And then the integral of 2 over x minus 1 is easy. It is 2 times ln absolute value of x minus 1. And also this one, negative ln absolute value of x plus 2. Notice that integral of 1 over x dx is ln absolute value of x plus c. And when you have ax plus b here, then the integral would be ln ax plus b over a, the coefficient of a, or the derivative of ax plus b plus c. So here, integral of 2 over x minus 1, 2 is a constant, you take it out, and integral of 1 over x minus 1 is ln absolute value of x minus 1. So if we can write rational functions like partial fractions like this, then we will be find their integral easily. So this is a rational function, p of x polynomial, q of x is also polynomial. Now let us differentiate between two types of rational functions, proper rational functions and improper rational functions. Well, proper rational functions, if degree of p is less than degree of q, if degree of the numerator is less than degree of the denominator, we call the rational function proper. Okay. And if degree of p is greater than or equal to degree of q, then the rational function is called improper. If the rational function is improper, we have to start by long division. Okay, if the rational function is improper, if the degree of the numerator is greater than or equal to the degree of the denominator, first thing to do to find the integral of this rational function is to use long division. Okay, and you write it like this. You write a p of x over a q of x as s of x, which is the quotient, okay, plus the remainder r of x over q of x. Well, let us take an example. Here we have a polynomial of degree 3 greater than polynomial of degree 1. This is a rational function, and it's an improper rational function. So we need to use long division. Let me remind you with long division. We write x cube plus x, okay? We divide this by x minus 1. We start by dividing the highest power here, the term with the highest power, x cube over x. When I divide x cube over x, I subtract the powers and I get x squared. I write it here. So first step is to divide. Second step is to multiply. Now I multiply x squared times x, I get x cube, and x squared times minus 1, I get negative x squared. Third step is to subtract. So DMS divide, multiply, subtract. Now to subtract, I change the signs of the second of this one, the polynomial here. So this was plus, I write it minus, this is minus, this is plus, and I can add now these two polynomials. When I add this, x cubed minus x cubed would be 0. I cannot add x with x squared. So I write first x squared, it's positive x squared plus x. This is the remainder, but the remainder has degree 2, so it's not the remainder yet. It's not finished. We will stop when we have something here less than the degree of x. Okay, we still, the rational function still improper. So we divide x squared by x. We do DMS again. Divide x squared by s, we get x. Then multiply x times x is x squared minus x. And then we subtract or we change the signs and add. When we add, we get x plus x, that's 2x. Well, not finished because I can divide 2x by x and get 2. Multiply 2x minus 1 times 2 minus 2. Change the signs and add. So when I add, I have 2. So now that's the remainder. So now I can write integral x cubed plus x over x minus 1 dx as integral of the quotient. Okay, x squared plus x plus 2 dx plus integral the remainder, which is 2 over x minus 1, the divisor, dx. Okay. So now it is easy to evaluate the integral. The integral of x squared is x cubed over 3. Integral of x is x squared over 2. Integral of 2x. And 2 can be taken out, and integral of 1 over x minus 1 is ln absolute value of x minus 1 and plus c. That would be the integral, the answer. Now we will start talking about proper rational functions. If the degree of the numerator is less than the degree of the denominator, what to do? Well, we have to factor the denominator. We have to factor the denominator. And when we factor the denominator, which is q of x, okay, the denominator, when the denominator can be factored as product of distinct linear factors. So each factor here is linear, okay? So for example, if you can factor, let us factor this denominator. This is I. Let me factor the denominator here. I have x squared plus 2x minus 1 over. Notice that this is a proper rational function. If I take x as a common factor, I will have 2x squared plus 3x minus 2. And this is degree 2. I can factor it easily. Okay. So 2x times x, and I have minus 2, so it should be negative 2 times 1. So I write it positive 2 minus 1. Now negative 2, negative 1 times 2 is negative 2, and the inner negative x, the outer 4x, 4x minus x is 3x. So this is the factored form. So we were able to factor the denominator into what? X times 2x minus 1 times x plus 2. These are three linear factors. X has power 1, okay? So this is what we mean here when we can write the denominator as a product of distinct linear factors. Distinct means different. These three linear factors are different because the 0 here is 0, the 0 here is half, the 0 of this factor is negative 2. So there are three different zeros or distinct zeros. Now, if the denominator can be factored into linear factors like this, distinct, then there is a theorem that says, the partial fraction theorem says, that you can write Rx over Qx like this. A1 up to AK are just constants. Okay, so I can write this rational function as denominator x, denominator 2x minus 1 and x plus 2, and here a, b, c, three constants. So this rational fraction can be written like this. Remember, this was, now we have this rational fraction and we would like to write it like this. So we need to find a and b. Okay, here we have a, b, and c. And now the question, how to find a, b, and c. And there are really different ways to find a, b, and c. And I will tell you uh, the first method, how to find a, b, and c. Well, the first method to find a, b, and c is to get rid of all the denominators by multiplying by the LCD. And the LCD here is x times 2x minus 1 times x plus 2. So I need to multiply both sides by x times 2x minus 1 times x plus 2. When I multiply the left-hand side by this, it will be cancelled with the denominator, and I will have x squared plus 2x minus 1. Now, the first fraction in the right-hand side, a over x. When I multiply a over x times this, okay, times, let me call it LCD, times the LCD, x would be cancelled with x, and I will have a in the numerator multiplied by 2x minus 1 times x plus 2 plus. Now the second fraction, b over 2x minus 1, multiply by the LCD. Well, 2x minus 1 would be cancelled with 2x minus 1, and I'll have b times x plus 2, the third fraction. C over x plus 2 multiply by the LCD. X plus 2 will be cancelled with x plus 2, and I will have c times x times 2x minus 1. So the first step in finding a, b, and c is to get rid of all the denominators like this. And now, what are the zeros of the denominator? We have x, the zero of x is 0. So I substitute with x equals to 0 in this equation. Let me call it star, okay? In star. So if x equals to 0, I'll have negative 1 in the left-hand side. In the right-hand side, 0 minus 1 is negative 1. 0 plus 2 is 2. Negative 2a, I'll have negative 2a. While here, if I put x0, this would be 0. And here also x0, so this would be 0. This term would be 0. This term would be 0. So these two terms would be cancelled, and I'll have just negative 2a equals negative 1. And when I solve this equation for a, I divide by negative 2, so a is half. So I found a quickly. Now what is the second 0? Okay, well, 2x minus 1. The 0 of 2x minus 1 is half. You put 2x minus 1 equals to 0. You take 1 to the other side, and then you divide by 2. So the 0 is half. Okay, so I replace x by half in star, in equation star. Well, half to the power square, this is 1 over 4, plus 2 times half plus 1 minus 1, that's 0. So the left-hand side is just 1 over 4. Now here, if I replace x by half, 2x minus 1 would be 0. So this term would be cancelled. The first term would be cancelled. The last term, also 2x minus 1, if I replace x by half here, this would be cancelled. And I'll have only this term. So replace x by half. x is half, and half plus 2 is 2.5. Multiply 2.5 times half, you get 1.25 or 5 over 4. So 5 over 4b. So 1 over 4 equals 5 over 4b. If you multiply both sides by 4 over 5, okay, you get that b is 1 over 5. If you multiply by 4 over 5, you have 1 over 5 here, and you have 1 here. Okay, so b would be 1 over 5. Now we found a and b. So what to do next? What is the third zero? The third zero, x plus 2. The zero of x plus 2 is negative 2. So let me replace x by negative 2. When you raise negative 2 to the power 2, and don't forget the parentheses, okay, you get 4, okay, plus 2 times negative 2 minus 4 minus 1. So the answer is negative 1. The left-hand side is negative 1. If I replace x with negative 2 in the first term, it will be cancelled in the right-hand side. Also in this term, it will be cancelled. But the third term will not be cancelled. I'll have 2 times negative 1, that's negative 2 minus 1, that's negative 3. Well, x is negative 2, sorry. X is negative 2. So negative 2 times 2, negative 4 plus minus 1, that's negative 5. And x here is negative 2. Negative 2 times negative 5, that's 10. So I have 10c, and c would be negative 1 over 10. And by this, I found a, b, and c, and I can immediately solve now the integral. So the integral I would be equal to integral of a over x, or a half over x dx, plus integral b is 1 over 5 over 2x minus 1 dx, plus c is negative 1 over 10 over x plus 2 dx, and I can find easily the answer here. Half, I take it out. Integral of 1 over x is ln absolute value of x. 1 over 5 can be taken out. Integral of 1 over 2x minus 1 is ln 2x minus 1 over 2. Remember, we divide by the derivative of 2x minus 1, minus 1 over 10 ln absolute value of x plus 2 plus c, and finally you can just write here 1 over 5 times 2, 1 over 10. Okay, and by this we solved this integral. So this method is an easy method. It worked well. It works well when we have distinct linear factors. Okay, and we can use this method quickly. Okay, we can find a, b, c here without doing all of these steps like this. Concentrate with me. It's the same method, but we do it without multiplying by the LCD. Okay, so concentrate with me. To find a, the 0 of x, which is in the denominator, is 0. So what to do? To find a, I replace x here in the left-hand side. In the left-hand side, to find a, I replaced x with 0, but without replacing this, because if I replace x, this x as 0, then the denominator will be 0. All right, so cancel this x and replace x here with 0. What do you get? 0 plus 0 minus 1, you get minus 1. 0 minus 1 is negative 1. 0 plus 2 is 2, so negative 1 over negative 2, or half, so a is half. Good. So this is a quick method without multiplying by the LCD. Now let us do it or try it with b. Okay, to find b, I cancel 2x minus 1. I have 2x minus 1. Below b, I cancel it. And I replace x here by what? By half. The 0 of 2x minus 1. Half 1 over 4 plus 2 times half, that's 1 minus 1, 0. And 1 over 4, 1 over 2, I replace x by 2. 1 over 2 times 2 plus 1 over 2, that's 5 over 2. If you use the calculator, 1 over 4 over 5 over 4, it would be 1 over 5. So b is 1 over 5, and we are able to find b quickly. Okay. Also c, you can do that. So we can use this quick method, and I will be always using it from now on. So for example, to find c, now what I erase, I don't use x plus 2, I erase it, and I replace x with negative 2 here by negative 2. So this would be 4 minus 4, it would be minus 1, and here negative 2 times 2, negative 4 minus 1, negative 5 times negative 2, that's 10. So c is negative 1 over 10 immediately. So this is how we find a, b, and c whenever uh, we have distinct linear factors. What if one of the linear factors or more than one repeated? Okay, so there is a repetition. Linear factors, but one of them is raised to the power 2, okay, or to the power 3. For example, here, look, x is raised to the power 2. This is a linear factor, x, it has a 0. I can find the 0. What is the 0 of x? It is 0. But x is raised to the power 2. X minus 1 is a linear factor. What is the 0 of x minus 1? It is 1. But it is raised to the power 3. Okay, so what to do? The theorem says in this case, you write x, a fraction for x, and a fraction for x squared. X minus 1 cube, a fraction for x minus 1, for x minus 1 square, and for x minus 1 cube. So, and you write always constants in the numerators, a, b, c, d, and e. So this would be the case if we have repeated linear factors. Let us solve this example. Well, notice here that the degree of the numerator is 4 and the degree of the denominator is 3. So this is an improper integral, improper rational function. Improper integrals are something else. And we have to use long division. Write in standard form, keep it in standard form, okay, large powers first. Now x to the power 4 divided by x to the power 3 is x. Multiply x to the power 4 minus x squared times x is x cubed. X times x is x squared. 1 times x is x. MDS multiply divide divide DMS divide multiply then subtract. I change the signs. This is plus, it would be minus, minus would be plus, plus and minus, and I add these two would be cancelled. And I have negative 2x squared positive x cubed. I cannot add these two. So I write x cubed first. Well, negative 2x squared, positive x squared. Yeah, I can combine these two terms, like terms. So negative 2x squared plus x squared, I have negative x squared. And 4x minus x is positive 3x, and I have plus 1. Can I continue? Yeah, x cubed divided by x cubed is 1. Multiply x cubed minus x squared minus x plus 1. Change the signs and add. These two will be cancelled. Negative x squared, positive x squared, also these two would be cancelled. 3x plus x is 4x. 1 minus 1 would be cancelled. Excellent. So I can write this integral as, this is I, okay. I can write it as integral of x plus 1 dx, that's the quotient, okay, plus the remainder, which is 4x over the denominator, x cubed minus x squared minus x plus 1 dx. Now it is easy to find, let me call this integral double I. It is easy to find the integral of x plus 1. But now how to find the integral of double I? I have a rational function. So I need to factor the denominator. How to factor the denominator? I have 4 terms. There is no common factor between the 4 terms. So I use factoring by grouping. I factor the first 2 terms together. I take x squared as a common factor from the first 2 terms. So I have x minus 1. X cubed over x squared is x minus x squared over x squared minus 1. I take minus as a common factor from the last 2 terms. So I have x minus 1. If I multiply negative x plus 1, I reach this one again. And now I have 2 terms and x minus 1 is a common factor. So I take x minus 1, the common factor between these 2 terms. I have here x squared minus 1. And now I can factor x squared minus 1 into x minus 1 times x plus 1. So I have x minus 1 linear factor repeated twice. So I can write this, or I can write 4x over, now let me write this in factored form. So I have x minus 1 repeated to the power 2 times x plus 1. Okay, so how to decompose this? I write it. I have x minus 1 squared, so I take x minus 1 and x minus 1 squared and a third fraction for x plus 1. So I'll have 3 partial fractions here. And here I have a, b, and c. And now I need to find a, b, and c. Well, pay attention. I can find b here and c, but not a, with the quick method. Okay, I can find b and c because b have x minus 1 to the power 2, which is already here also. Okay, so to find b, I cancel x minus 1 square from this, the left hand side, and I replace x by 1. When I replace x by 1, I have 4 over 1 plus 1, 2. 4 over 2 is 2, so b is 2. All right, good. Now, how to find c? Well, the 0 is x minus 1. So I erase x plus 1, sorry, not x minus 1, erase x plus 1. Yeah, and replace x by minus 1. Negative 1 times 4 is negative 4. Negative 1 minus 1 is negative 2 squared is 4. Negative 4 over 4 is negative 1. So c is negative 1. Okay, how to find a then? Well, there is no, yeah, putting the zeros here is not helpful. So let me first multiply by the LCD and get rid of the denominators. When I multiply by the LCD, notice the LCD here is what? Is always the original denominator. The LCD is x minus 1 square times x plus 1. Okay, I will multiply both sides by this. So I'll get immediately 4x equals a times what? X minus 1 will be cancelled with one of these, and I still have x minus 1 times x plus 1. Plus b now is 2, okay? 2 times x minus 1 squared would be cancelled, and I'll have x plus 1. C is minus 1, so minus x plus 1 would be cancelled, and I'll have x minus 1 to the power 2. Now here, the easiest way to find a is to replace x by any number you like. Okay, so let me, for example, but not, of course, not 1 and not -1, other than the zeros, because -1 and 1, we used them to find b and c. So put x0, put x2, whatever you like. If I put 0, 4 times 0 is 0, the left-hand side is 0. 0 minus 1, -1, 0 plus 1, 1, so negative a. 0 plus 1, 1 times 2, so that's 2. 0 minus 1, -1 square is 1, so minus 1. So a, I can take a to the other side, and I have 2 minus 1, which is 1. So a is 1. I have a easily. So a is 1, and now I can write the integral of I. I can solve the problem. Well, I equals integral of x plus 1. Let me write it, okay? Integral of x plus 1 dx plus now the double I integral. So it is integral of a is 1, so 1 over x minus 1 dx. b is 2, so integral of 2 over x minus 1 square dx. c is -1, so I can write -1 over x plus 1 dx. Okay. Well, we know how to find integral of 1 over x minus 1, x plus 1. But what about the integral of 2 over x minus 1 square? Well, we know that integral of x to the power n is x to the power n plus 1 over n plus 1. So if we have, instead of x, if we have ax plus b to the power n, also the integral would be easy. It would be ax plus b to the power n plus 1 over n plus 1, but we need to divide by a, or the derivative of ax plus b. So that would be the integral, all right? Of course, there is a plus c always. This would be the integral. So this one, I will write it x minus 1 to the power -2. So I will write it like this, okay? So the integral would be integral of x is x squared over 2, integral of 1 is x, integral of 1 over x minus 1 is ln absolute value of x minus 1. And now here I have 2, and integral of this one is x minus 1 to the power -1 over -1. So there is a -1, and x minus 1 to the power -1, I can take it down, okay? And the integral of x plus 1 is 1 over x plus 1 is ln absolute value of x minus 1, sorry, plus 1 plus c. That's it, okay? If you want to write it, x squared over 2 plus x, here -2 over x minus 1, and here ln minus ln, if you want to write it, ln absolute value of x minus 1 over x plus 1, because ln minus ln is ln like this, quotient, okay? Quotient changes to negative. That's okay. That would be the final answer. Also this answer is acceptable. Third case. What would happen if Qx contains irreducible quadratic factors, none of which is repeated? So no repetition, and the factors are not linear. The factors are irreducible, like this. How to know that this degree 2 is irreducible? You find the discriminant, okay? If the discriminant is less than 0, then this degree 2 polynomial has no real zeros. So it would be irreducible on the real numbers, okay? So, for example, if we have this rational function, notice that this is a linear factor. Here we have an irreducible quadratic factor, and this is irreducible quadratic factor. It has no real zeros, okay? So we write it a over x minus 2 as usual, but the irreducible quadratic factor in the numerator we write ax plus b, all right, degree 1. So we have a here, so we write here bx plus c, and here dx plus e, because this is an irreducible quadratic factor. We will need this formula, okay, dx over x squared plus a squared equals 1 over a tan inverse x over a plus c. We know before that the integral of 1 over x squared plus 1 dx is tan inverse x plus c. But now what if it is not 1, it is a squared? So also it would be tan inverse, but we have 1 over a and x over a here inside the tan inverse. Let us evaluate this integral. First step, as soon as I see a rational function, the derivative of the denominator is not in the numerator, so I cannot use the usual substitution. I factor the denominator. So let me factor the denominator. Let me call this I and factor the denominator. If I take x as a common factor, I will have x squared plus 4. Well, x squared plus 4 is an irreducible quadratic factor. So I have 2x squared minus x plus 4 over x times x squared plus 4. And now I want to write the decomposition as partial fractions for this rational function. I have a linear factor, so I write a over x. Here, this is an irreducible quadratic factor. So I have bx plus c, linear factor in the numerator. Now, how to find a, b, and c? Well, b and c, we cannot use the quick method to find them, but I can use the quick method to find a. I cancel this x, and I replace x with 0. So 4 over 4, so in fact, a is 1, okay? As quick as that. And now let me multiply by the LCD. And the LCD here is x times x squared plus 4. Okay, so the left-hand side would be 2x squared minus x plus 4 equals. Now I have 1 over x. When I multiply by the LCD, x cancels with x, and I have 1 times x squared plus 4, or just x squared plus 4 plus bx plus c times. When I multiply this fraction by the LCD, x squared plus 4 cancels, and I still have x. Good. Now, I don't have variables here, no coefficients in x squared plus 4. So I will take it to the other side. 2x squared minus x squared would be x squared, and I have minus x, and 4 minus 4 would be 0. And here I have bx times x, bx squared, and cx. Now, the third or the second method we usually use to determine the coefficients a, b, and c is to multiply by the LCD and then write this as a polynomial, usual polynomial in the left-hand side and in the right-hand side. And then these two polynomials are equal, so the coefficients should be equal. I mean, the coefficient of x squared here should be equal to the coefficient of x squared in the left-hand side. So b should be 1. And c, the coefficient of x should be equal to the coefficient of x in the left-hand side. So c is negative 1. And so I have now, I can write I, the integral of I as integral of a over x is 1 over x dx, and plus b is 1, so I have x, c is negative 1 minus 1 over x squared plus 4 dx. And now the derivative of x squared plus 4 is 2x, but I have here x minus 1. So to use substitution, I do it like this, integral of 1 over x dx. And here I write it x over x squared plus 4 dx minus 1 over x squared plus 4 dx. So I distribute the numerator over the denominator. Now, the derivative of x squared plus 4 is 2x. So I need 2x in the numerator, so I have 2 here and 2 here and half here, so I can use usual substitution. I can take u equals x squared plus 4, and then du would be 2x dx, and then this integral in the middle would be half integral du over u. So the answer would be half ln absolute value of u, or absolute value of x squared plus 4. So the answer would be, the final answer, integral of 1 over x is ln absolute value of x. This one half ln absolute value of x squared plus 4. And here we will use this formula, x squared plus 4. So the integral would be 1 over 2 tan inverse x over 2. So negative half tan inverse x over 2 plus c, because 2 is the square root of 4. Okay, a is the square root of a square. The last case, if qx, when we factor qx, we find a repeated irreducible quadratic factors. Okay, so we do the same. We, like here, for example, we can write this as a over x, because x is linear, b over x minus 1, because x minus 1 is linear. And now x squared plus x plus 1, if you find the discriminant, b squared minus 4ac, it would be negative. So I will write cx plus d over x squared plus x plus 1, because it is an irreducible quadratic factor. But qx squared plus 1 is also a irreducible quadratic factor, and it's raised to the power 3. So a fraction for x squared plus 1, a fraction for x squared plus 1 square, and a fraction for x squared plus 1 cube. Okay, and here I write ex plus f, gx plus efgh, whatever lx plus m. Okay, and I find all of these coefficients. But he said here, write out the form of the partial fraction decomposition of this function. I will continue this video because it's too long now in another video, so I will stop here. Thank you very much.